Okay, welcome back. Our second speaker is Martina Lanini, and she'll be telling us about GKM theory for cyclic quiver Grassmannians.
Thanks so much. Thanks so much to all the organizers. It's a great pleasure to be here. What I'm going to tell you about, I'm going to try to advertise two things, which are mainly GKM theory, which I know some of you know already, but I don't think all of you, since it's so diverse, this audience. And it's something which is really sort of my first love. So since my PhD thesis, I've been playing with that. So it's really fun, it's really pretty, and you can really compute with that. And so that's going to be, I guess, the main focus of the talk at the end. And then I want also to talk a little bit about this, which are very nice varieties. Just let me tell you this, in the sense that you can describe them in linear algebraic terms, so they're in some sense extremely explicit. And so I had for ages this sort of dream of like merging these two theories. And so finally at some point I managed to hire a postdoc, which is Alex Puetz, who was, knew very much quiver Grassmannians, and so we managed to bridge these two words. And that's it, sort of a starting point, as you'll see. So what's the idea? So let me give a little bit of an idea of the GKM theory. So what we have, let's say X, with some complex projective algebraic variety. And in fact, I'm already restricting too much. So I decided, because of this, since I will care about applications in there, we are going to focus on complex projective algebraic varieties. But in fact, the theory I'm going to talk about works in a way more general setting. Or whatever. We have X. Doesn't need to be smooth. Doesn't need to be normal. And then it is acted upon by an algebraic torus. So let me say this first very vaguely. So if this action is nice enough. So what the main slogan of GKM theory is that we have our complex projective algebraic varieties, this torus acting on it. And so what we can do is to study sort of local behavior of the torus action. So let's say local information, meaning we can look at fixed points. We can look at one-dimensional orbits. Well, and from this, in fact, we get global information. Okay. And again, what do I mean by this? So for example, so from this local information, we can compute cohomology of X. More precisely, equivariant cohomology. But, well, in fact, if X is smooth, you can generalize this and use local information to compute generalized cohomology theories. So, I don't know, equivariant K-theory and so on. Or you can, if your X has even more structure, so for example, has a Whitney stratification, which is T-stable, you can use that to compute intersection cohomology. So somehow that's, for me, the way I started looking at this. Okay, so let's try to say what is nice enough. Okay, so this is somehow what we want to do. So we want to, first of all, say what nice is, and then try to see what this means. So to compute some equivariant cohomology by using local information. So let me give an ad hoc definition, maybe here. So I'll define the notion of GKM pair. So maybe let me also say what GKM stands for. So it's Goresky-Kottwitz-MacPherson. So once again, we're looking at a way bigger class of varieties than the ones I'm going to talk about. So we say that a pair xt as before, so we have a complex projective algebraic variety x and an algebraic torus acting on x, is a GKM pair if, well, first of all, I have, let me say, T equivariant embedding of x in some big projective space. Well, projective varieties, of course, I have an embedding, but it's compatible with the torus action I picked. So if there is a T equivariant embedding x in some Pn. Well, okay. Then I want to say something about local things. So again, very much more restrictive, but I'll take finite number of fixed points. Okay, you can extend this to discrete set of fixed points, but for today, that's what we're going to do. Then we have a finite number of one-dimensional orbits. Well, in fact, this would be enough, because fourth thing I'm going to list, in fact, follows from these three. But I want it here so that we have it on the board, which is, okay, what do we have? We have these one-dimensional orbits. So since T is an algebraic torus, this will be some C star. And what happens is that if I close it up, because of this embedding, it's going to be just a P1, and in the closure you have two fixed points. Okay, but I want to write it down so that we can visualize it. So now the idea is that you have the torus moving around the points of your x, you have some fixed points, and then they want to look at one-dimensional orbits. Okay, but to any one-dimensional orbit, you associate, so it is uniquely determined by the two fixed points in its closure. And so in fact, you're sort of drawing a graph. Okay, so that's the idea. Let me write it down. So, or maybe we can just say, so if we take O, one-dimensional T orbit, then the closure of O is O with two distinct fixed points. And it is really like Q1. Okay. So this is sort of what we need. Let me, since we have all these boards, I can have examples here. So, so first example is what you would expect is just P1. Okay. So let me take X is P1, and then, well, let me act with like two copies of C star, just very scaling coordinates. Okay. So, okay. This is, I mean, we're sort of rotating our P1. Okay. And we have two fixed points, which are just 1, 0, and 0, 1. Okay. Let's call it 0 and infinity. And then, of course, we just have one-dimensional orbit, which is the orbit of 1, 1. So the only one-dimensional orbit is the orbit of all other vectors, of course, which means pairs, so A, B, such that they're both non-zero. Okay. Yeah?
So are you disallowing if 0 and infinity coincide to get like a...
No, this cannot happen.
Okay.
So yeah, here maybe you can see it, but somehow if you have this equivariant embedding, so either this or you take it as a third requirement about this action. So again, as I was saying, you can generalize this to, and this is really what you need. The important things are finite number of fixed points, finite number of one-dimensional orbits, and close the orbit up, and you get two fixed points. And in fact, here we can see it. So, well, if you take the closure of this, I mean, this is the C star here, So we remove these 2 points, when you close it up, you get all your P1. But, so let me do, maybe, yes, good. So let me do very quickly example 2. I don't want to say too much. Is just another important class of varieties, which are varieties of complete flags in Cn. Okay, so this is just chains of nested subspaces of Cn, Vi of dimension I. So this is, I mean, we saw already in Paulo's talk that if we take the affine space, if you take a n, you can act by an algebraic torus just by rescaling coordinates, right? So that's exactly what you do here. You can act by rescaling coordinate on Cn, and this is, of course, some linear action, so all inclusions are preserved. So you have an action of C star n. So whenever you, let's say, you fix a basis, it's really just rescaling coordinates. Okay, so we have this action on FLN. And now exactly as in P1, which is a very special case, it just lines within C2, so it's baby flag variety, so FL2. If you look at fixed points, you just get all coordinate vectors, 1, 0, 0, 0, 0, or, yeah, sorry. We think about flags. So what you do, you do the same thing as before, and so you see that V1 can have only one non-zero vector, non-zero entry if it's a fixed point. And then you go to V2 and you realize that this can have, must be the span of 2 vectors, so the basis is fixed, and so on. Okay. So what happens, I just want to tell you the combinatorics, is that if you look at fixed points here, these are parameterized by permutations. Okay. And if you look at one-dimensional orbits, these are, so we said that an orbit is just uniquely identified by a pair of fixed points. And so here you have pairs of permutations where the second one, where there exists a transposition ij, well, in a sense, of course, so that tau is ij sigma. Okay. So again, I mean, you can just, if you haven't ever seen it, you can just take FL3 and check it. And it's an easy exercise, but what's nice is that you really see some algebraic combinatorics appearing. So that's a symmetric group, and that's this requirement about transposition. Okay,
so
and it's,
what's
yeah.
the action exactly?
Oh, the action is just this. So you are, so this, let's say, identify this C star to the n with diagonal, if you want, diagonal matrices in GLN.
Yeah.
And then GLN is acting here, it's linear, and so it preserves certain inclusions.
Perfect.
Or just you fix a basis, and this is rescaling. So the ith entry is rescaling the ith coordinate. Sorry, it was a bit quick. But again, so this is again a very special example. You can generalize it to any flag variety. So you can take an algebraic group and some parabolic subgroup. So you have this homogeneous space. You have again the maximal torus of the group naturally acting on it. Fixed points are parameterized by Val group elements. Well, it depends on the parabolic. So some cosets in the Val group. And then again, you have a condition similar to this. Okay, so it's very pretty. Somehow you're jumping from geometry to algebraic combinatorics. Okay, what do we do with all of this? Okay, so we want at some point to compute something, and so first of all, let me say something I said already, that if you have a GKM pair, then this, as we noticed already, produces for you a graph, okay? A moment graph, which has as vertices, we said fixed points And now I write edges here. I want to write something else here. It's not enough edges for me, but for the moment, so edges are nothing but one-dimensional torus orbits on X. But in fact, now let us look at these one-dimensional orbits. Okay, so as we noticed, if, let's say, O is a one-dimensional orbit, well, this has to be isomorphic to C star, right? Okay. Okay, but then, so here we had the T action. We can just translate, I mean, this T action, so this C star gets a structure of a T space, right? So what does this mean? So this is a T space under this isomorphism. And at that point, well, you have an action of T on C star. So it has to be given by a character of the torus. Okay. So what's happening is this. Since this is a T space, then there exists an element of the character lattice of the torus. Okay, so here we have homomorphisms of algebraic groups, meaning it just here we said it's certain number of copies of C star. You want to get a non-zero complex numbers, so you're just sending this tuple to first thing to the some power times second thing to the second power and so on. So it's really a lattice. It's isomorphic to Z to the rank of the torus. Anyhow, so what we're saying, this is a T space, so meaning that there exists a well-defined characters once this isomorphism is fixed, such that for any T in T and for any complex non-zero complex number Z, Tx as multiplication by alpha T. Okay. I'll give you an example if it is unclear. Okay. So this is our one-dimensional orbit here, right? So well, and here, so you'll see that there's some dependence on this isomorphism we fixed, which is not very important though, it's just a sign. So let's say, so this is a C star, and for example, I can get the isomorphism just sending, the point AB to AB inverse. Well, in fact, I have only another one possible isomorphism, which sends AB to A inverse B. Okay. But anyhow, let's stick to that. Okay. So well, the inverse of this isomorphism is just I take a complex number and it goes to Z1. Right? Okay, now I want to understand what my alpha is. So what do I have to do? I take my T structure on C star, T variety structure on C star. Okay. So I take my element Rs and I act on Z. Okay. So it's for any Rs, for any Z, etc. So what does this give me? Well, I'm copying, I'm inducing the action from the action of T on P1. So this corresponds to Rs acting on Z1 if you want, and then I go back to C afterwards. Just visualize what's happening. And here we said first entry is rescaling this, and second entry is rescaling that. So this is RZS, right? But then I want to go back to C. So this is nothing but R S inverse Z. Okay. So that means that I found alpha. Alpha is the homomorphism which goes from two copies of C star to C star and takes RS ascending to RS inverse. Okay. So this is something that, yeah, maybe since later I'll use it. Epsilon 1 to this epsilon 2, where whenever you have some algebraic torus, this is the basis of the torus character. Send a tuple T1, Tn to Tk. Okay, so it's just a basis for their home space. But yeah, the observation is exercise. If you do the same with this other isomorphism, well, I mean, you run the same thing, then the homomorphism telling you back, taking you back from C star to O is sending Z to 1Z. And so what you'll get here is SR inverse, meaning that this is minus this character. But we'll see that it's not very important this time. Okay. So, but what I wanted to do, that was all this chatting more for this, is that I'm not happy enough with just a graph. I want to label the edges of the graphs. I want to color them. And I do it by torus characters. Okay, so I say, okay, for up to a sign, these are uniquely determined. I pick one. I like plus more. I pick the one, the one coming from the isomorphism I preferred, and I color the edge. Okay. Let me say X, T, label edges. So whenever I have O, I send it to, let's say, X, Y, alpha O, where O bar is O. Union X, union Y. Okay, so the notation is, if I fix an orbit, the corresponding character I've picked is called alpha O. Okay. We're almost there. So now I want to use this graph. So now we'll show, I will tell you that you can compute equivariant cohomology just by using this data. Okay. Oh, yeah, so for example, there I wrote everything a bit too big. But so for example, if we have our P1 example, as before, so we got this graph, 0, infinity, epsilon 1 minus epsilon 2. Okay. Okay, so now again, we want to compute it. So let me introduce this one piece annotation. So again, I'm not sure whether everybody's familiar with equivariant cohomology. I think maybe a big bunch, I'm not sure. But anyhow, so if you are not, if you have never seen it, so just take the theorem I'm going to give you as a definition, because it's really pretty. So we'll see that, so via this theorem, in this nice situation, your equivariant cohomology can be described by sort of graph combinatorics and commutative algebra at the end. Okay. So we'll see. So let me just say, I'll denote by S the equivariant cohomology of the point. And if you're not familiar with that, this is just a polynomial ring. So it's the best thing you can if you want. So, and also let me say that for me, this means, or whatever I have here, is with rational coefficients. I mean, for flag varieties, actually you could even use that, but just to make sure. So this is, in fact, you can identify this thing with Q epsilon 1 epsilon n if T is a rank n torus, okay? Where these epsilon are the ones we said there. So what this is just, if you like it more, this thing is just a lattice. So we said it's Z to the rank of the torus, so to the n. And so what you're taking, you're extending scalars. So you replace that by Q, and you get a vector space, and then you take the symmetric algebra of this vector space. And this epsilon is just because you are somehow, you did some identification between the Hom space and Zn, the Hom module and Zn. Anyhow, polynomial ring S. Well then, what else you should know? You should know that HT has functorial properties, okay? So in particular, well, of course, we always have an inclusion. So, no, I wonder, sorry. We always have, this is gonna come later, a projection of X on a point, Okay, so this is a contravariant functor, it's cohomology. So this gives us, in fact, a map from our S, so our polynomial ring, to the equivariant cohomology of X, which makes this guy into an S algebra. Okay, so that's the structure. And then I also want an inclusion indeed, but not only a point, I want all my fixed points. Okay. So in fact, whenever, again, I have my torus action, I can look at the fixed point locus. This is clearly included in X. And again, HT is functorial. So this was I get a map of S algebras from HTX to HT of my fixed point locus. Okay. So well, now, if we are in the nice situation, also if the fixed point is discrete, so these points don't talk to each other. So this is nothing but the direct sum of the equivariant cohomology of the point for each of the fixed points. So I have as many copies of my polynomial ring as my fixed point. Okay. Okay. So here that's our commutative algebra appearing. Yeah, let's say we call it I upper star. Now, do I have enough room, or should I need? Yeah. Let me go to a new board. Can you all read here, or that's okay? Cool. Okay, so now, so somehow what the theorem says that I'm going to write down is that, well, that S algebra map, I upper star, is injective, and we can explicitly describe the image. Okay, so if we take a GKM pair, of course. Okay, and so at that point you can identify HTX with the image of this map, and that's a way of computing it. So this is, let's say, is attributed to GKM. It is indeed in their paper, but in fact, this very specific statement, well, maybe more in the analytic category, but whatever, appeared already way earlier in Chang Skjelbred paper in '74. Okay, so, but somehow.
Well, I think the big thing for GKM is they point out that this actually you can actually use this. You can actually compute with it and stuff.
Yeah, but somehow what I'm going to write down is yeah, exactly.
But the fact that it actually gives you a way to compute it applies to many things was
this is true. That's in fact but on the other hand,
because no one knew about that work for a long time.
Apart from Dave Anderson, which is always like. You should reference
okay. So before Dave Anderson has a PhD, some people knew about it, but they didn't know about it before GKM.
Yeah, but it's a sense. Yeah, absolutely. Yeah. In fact, this paper contains way more than this theorem. So that's. I mean, I really want to make this point. So this is a tiny bit of the paper that I have, which is about Kosudio. I mean, it's way bigger thing. But somehow what we need is this. So let's take a GKM pair. Well, then I upper star is an injective map. So just an observation. So there we have this direct sum of S's. And so what's the structure of S algebra, where you can multiply and add on any summand, and then you can just diagonally act by S. Okay, so that's the structure of S algebra we have. And so, and its image is the following. So now we are within a direct sum of polynomial rings. So So we have one polynomial for any fixed point, or if you want, one polynomial for any vertex of our graph. And now we want to use the edges and the labels on the edges to glue this data together. Okay? So we're going to get from the edges some compatibility conditions. Okay? So whenever we have an orbit whose closure is O together with X and Y, or if you want, whenever we pick an edge in the graph, here the condition is that Fx is the same as Fy if we consider them modulo the label. Okay? I'll make an example so it becomes clear. So again, X is varying in the vertex set. And then we have, whenever you have two vertices adjacent to the same edge, you look at a corresponding pair of polynomials, then that edge had a label. But now, by the identification upstairs, so our labels are polynomials in torus characters, then you can make sense of this. So you're saying that these are two polynomials which are the same modulo that torus label. So let's see. I did very badly here. So maybe I can just do it here. We have enough room. So let us look. Let us look at P1 example. We have our graph. Okay. So now this tells me that if I want to compute my T-equivariant cohomology of P1, I mean, I can identify it under the above, let's say it's isomorphic, to the following S algebra. So we have pairs of polynomials. So F0, F infinity. Now S is Q epsilon 1, epsilon 2, so it's polynomials in two variables. And here what I want is that F0 is the same as F infinity modulo epsilon 1 minus epsilon 2. Okay? So another way of saying this is that here F infinity, so I have F0, and then F0 plus epsilon 1 minus epsilon 2, G infinity, or F0 and G infinity vary in S. Okay? So, well, saying that these two are the same modulo epsilon 1 minus epsilon 2 is exactly this, right? So the difference is just a multiple of this torus character. Okay? And so if you now remember what the S algebra structure was, you just see that this is nothing but F0, which rescales 1, 1, and then G infinity, which rescales 1, epsilon 1 minus epsilon 2. Okay, and then you vary these polynomials in S. So this is just to tell you that, oh wow, so we found indeed a generator, and here I forgot to say something there, in degree 0. And then we found a torus character here, which in fact has degree 2. So this is something being too quick here. So this is an identification, and we want everything to be graded. So you should say what degree your variables have. And these are all degree 2. So why am I making this point? So I want you, again, to observe what we got here. So here we got, by applying our theorem here, that the equivariant cohomology of P1 is a free S module of rank 2 with one generator in degree 0 and one generator in degree 2. Okay. So and this is, in fact, what we can do now is a free S module. I can kill this equivariance. So I can go back to Q coefficients instead of S coefficients, and I get back the usual cohomology. Okay? In fact, cohomology of P1 is just one generator in degree 0 and one generator in degree 2. And also multiplication is compatible with that. Okay. So that's, well, that's an important feature of these GKM spaces, which are so-called equivariantly formal. And in fact, so if you're not interested in equivariant cohomology, you can still use this machinery to get the usual cohomology back. Okay. So, and again, here you can play a similar thing with flat varieties, which, okay, so let me see. Oh, okay, I'm doing fine. So, okay, before moving to quiver Grassmannians, let me tell you why is that good. So, I mean, so having such an explicit description, of course, allows you to make computations. And in some sense, maybe it's a bit upsetting. I don't know, I always wondered why. But somehow it has been extremely exploited, this description, for flat varieties. And that's, again, the way I got to it. So it's very, this description was, so allows you to, I mean, to get results in Schubert calculus, which is in some sense not that surprising because it's really about cohomology classes. But also what you can do is to, so you get, since you can play with flat varieties, you get plenty of applications in geometric representation theory. So that's a sort of an upgrade of this theorem, which is about equivariant intersection cohomology. This is, I mean, it was already in GKM, already they observed that you could apply it to intersection cohomology, but then somehow some sort of explicit algorithm to compute it for flat varieties and a certain big class of varieties was found by Braden and MacPherson. And this was sort of very lucky because then somehow was applied by Fiebig to find some alternative proof to the Casa-Lucy conjecture about characters of representational complex finite dimensional Lie algebras. You can use it also to study intersection cohomology and characteristic P, and so on. So, but it was extremely applied for flat varieties. And somehow, I mean, while it works in a way more general setting, and so that was somehow the motivation of all of this, to say, okay, can we, I mean, find another class of varieties which is somehow relevant and where, I mean, again, we know that a priori it's a big class, but is there another relevant family for which we can indeed show that we have a GKM space and we can run this thing? And so I'll tell you what this family is. So, I mean, one of the families.
Of course, it gives you what we know for toric varieties. So
Yeah.
that was,
This
and many spherical varieties have this as well.
Yeah. Yeah. It's true. Yeah. Yeah, this is very much correct. Let me also say, maybe I was hiding this, but a class of varieties motivated by representation theory. So, which of course also toric varieties are. But somehow I was always a little bit upset about this, just flag varieties, Schur varieties, and so on. Also, let me mention that, so having such an explicit description allows you to realize, so that's work, for example, of Giuliano Timotsko, which allows you to realize on equivariant cohomology of Schubert varieties some actions of Wald groups. Very explicitly and to study that. Or allows you to have, again, a very good control of equivariant Schubert classes, which means, in some sense, a basis or, well, a set of generators for your homology. And it's a big problem in Schubert calculus, for example, to study structure constants. And when hope is that you can move to equivariant and play with in the equivariant setting and go back. But anyhow, so let me tell you what these quiver Grassmannians are. So again, quiver, that's a big community like working on quiver Grassmannians, and it involves a lot also of representation theory of quivers, which of course I can't discuss now. So what I'm going to do to present this part of the talk is just focus on this cyclic quiver case. So in general, well, a quiver is nothing but an oriented graph. And a representation of a quiver is nothing but a configuration of vector spaces and maps among them, which are somehow controlled by the shape of the graph you have. Okay? But for us, the quiver is very special, so we can just write down explicitly what we have. Okay. So cyclic quiver. So the quiver we look at is the following. So now it's like different topic, and I will merge at the end. So maybe spoiler already is that you can keep the varieties you're going to define with a GKM variety structure. So just in case you get bored before the end. So we starting point is a graph. We have an n fixed, and we look at the cycle, equivariant cycle over n vertices. Okay, so I have n vertices and an edge from I to I plus 1, where I plus 1 means modulo n. And now I want, again, what's called delta n representation. Again, it's just a bunch of vector spaces and maps. So will be something like this, and now we can formalize it. So we want some finite dimensional vector space on the first vertex. Then I put the finite dimensional, everything is complex, C vector space on the second vertex. Then I get the third here, fourth, until the nth, all finite dimensional vector spaces. Okay? And then I follow the arrows, and then I say, okay, I have also to define a map of, C linear map between M1 and M2. Then I have to define a map between M2 and M3, and so on. So one compact way of saying this is that we have a Zn gradient vector space, C vector space. So this Mi is a finite dimensional C vector space. And then we have a map. We have a map which is K-linear of degree 1. Degree 1 modulo n, though. So this is a KC. Of course, you can define everything for any field, but for us, so it's a C-linear map, which has the property that takes the ith keys of M and send it to the I plus 1. Where, again, so if here we have Mn, this is M1. Okay, so indices are modulo n. Okay, so this is what a representation of a quiver is. And so what we want to define is the notion of a Grassmannian of this thing. Okay, well, so what's the classical Grassmannian? You have a vector space that you fix, and now you look for subspaces of a fixed dimension. Okay, so this is what we would like to do. So to say, okay, I fix, well, at this point is not a dimension, but I have to fix some dimension vector. So I'll say 1, 4, 7, 9, something like this. So I fix a dimension for any vector space I have. And then I would like to take a collection of subspaces. Fine. But then I have to remember that I don't only have a configuration of vector spaces, I also have maps. So what we'll do, I write a definition. What we'll do is, so a point in our Grassmannian will be a collection of subspaces, one for each of the spaces I fixed, which are compatible with the maps. Okay, I write it down. So we fix some vector E in M. Okay, so it could be also 0 some of the entries. but it's a bit boring. And now I want to define, so I take a delta-n representation and I want to define GRE-M. Okay, so that's going to be the associated quiver Grassmannian of dimension vector E. So in here, what I'm going to get, so is a collection of subspaces, so Ni, yeah, I and Zn. In fact, I can also, let me express it as a graded vector space. But nothing changes. So where each of these Ni is a point in the usual Grassmannian for Mi, okay, of a dimension I fixed. And then I had my map phi, have my map phi here, from my ambient Zn gradient vector space to itself. And I want that it takes this subspace to the following one in the configuration. Okay. So again, intuitively, it's a collection of subspaces which is compatible with the maps I fixed. I mean, in general, you have whatever graph you want. The representation will be a configuration of vector spaces. You will have the maps, and you can imagine what the corresponding quiver Grassmannian is. It's again subspaces which are compatible with the collection of maps you fixed. Well, okay. So now so this is called quiver Grassmannian. And now, by the very definition, this lies within this product of classical Grassmann varieties. So I use this part of the definition. And now this condition here is a closed condition. Okay? So this guy inherits a structure of itself complex projective algebraic variety. Which is in general singular. So for example, it's the first difference with the flag variety. I mean, I mentioned already sugar varieties which are in general singular, but we didn't see an example. So in general singular. And also in general can fail to be normal. In general. It doesn't need to be normal. So that's somehow a lot of I don't know, properties we usually, I don't know, exploit are not bad. Anyhow, so let me say, so maybe one thing I said, you can define everything in a way more general setting. And in fact, it's sort of very natural to try to restrict to specific classes of quiver Grassmannians, because by a result of Reinecke, in fact, every complex projective algebraic varieties can be realized as a quiver Grassmannian for some quiver. Okay, it's a very short paper, 2 pages, and the quiver is extremely ugly. So I guess, as far as I remember, it's 2 vertices and plenty of edges. This is really, really bad. But the nice thing in this case is that the quiver is pretty nice. And in general, I mean, you would have this very ugly description as a quiver Grassmannian, but if you're lucky and you manage to realize a variety you care about in terms of a nicer quiver, so this is not a unique, of course, realization, then you might be able to use techniques coming from quiver representation theory to attack geometric problems. Okay, so that somehow will be the idea. So let me give you some examples. So since I'm talking about delta n, the first sort of zero example is the following one. Let us look at delta 1 as a sort of a loop. So let us look at as a representation, the one having, so I just need one vector space and one map, one endomorphism of the vector space. So I take Cn, and here I take just the zero map. So in fact, this is a representation of a point, of a quiver with no errors, but whatever. Okay, and now I want to pick a dimension vector. Now I need, well, one number. Let's call it D. And now it's immediate to say that somehow this is the zero map. So whatever d-dimensional subspace of Cn I'm going to take is going to be sent by the zero map to itself. So that means that in this case, our GKM is just the usual Grassmannian of d-dimensional subspaces of Cn. Zero example. Then we can, well, let's look at this other example. So let us take a property of n. So we have n vertices. And now, so let me put Cn plus 1 on all of them. Okay. And then let me take identity map here, identity map here, identity map here, identity map here, 0. Okay, for who is familiar a little bit with quivers, I mean, whenever I put a 0, it's like if the arrow wasn't there, so it's really a representation of A and quiver. Aha. Okay, let's call this M. Now I have to pick any. I take 1, 2, 3, n minus 1, and okay, I needed n integer numbers. Okay. Okay. Let us look at EM. What do we need? So now we need, for any I need a subspace of Cn plus 1. I write it this way. So for any, well, let me say it out loud first. For any I need a subspace of Cn plus 1, which is such that of dimension 1, 2, 3, 4, up to n. And then, so let me say I take my ith vector space, which has dimension I. I take the I plus 1, which has dimension I plus 1, and here I is less than n. And now the condition of the map, what is this telling me? It's just telling me that the identity map applied to n1 is contained in n I plus 1. Okay? So this is the flat variety again. So this is really just FL, but n plus 1. So, well, second example, so the 0 doesn't count. So what you can do, you can take the same representation, almost the same representation we had in 1, but sort of change the maps on the non-zero, so change the non-zero maps. Okay? And so if we modify M from 1 by taking whatever linear map you like, by changing the non-zero maps. So we get something which is called linear generation, maybe one generation of FL m plus 1, which were studied a lot by Cerulli, Frank, Fagan, Fourier, and Reinecke. So here I wanted to mention this because somehow that's, well, they have plenty of papers about this, and you can really say a lot just by looking at the representation theory side. So for example, there's, again, a big family of the generation of the flag varieties, and you can give conditions on the rank of the maps, or the concatenation of the maps, to say exactly, for example, when this degeneration is flat, or when the degeneration is irreducible. And this is really based on quiver representation theory. Well, that's, yeah, but these maybe are not that convincing because we're still sort of representing the type A quiver. Well, let me just say it while I clean up a little bit out loud. So there's plenty of interesting proper representation of delta n. So for example, you can use quiver representation to give finite dimensional approximation of the affine flag variety or the affine Grassmannian, in the sense that you can construct both varieties as in variety having as pieces exactly these finite dimensional approximations. Well, we have a series of papers with Evgeny Fagin and Alex Puetz on a specific class of representations of delta n, which are related to totally non-negative Grassmannians on one side and local models of Shimura varieties on the other side. But anyhow, it's a very rich class of varieties. This was just you can realize plenty of Schubert varieties in this way. Not all of them, but that's a big class of Schubert varieties you can realize as, even in the affine flag variety, as quiver Grassmannians for the equivariant cycle. Okay, so I'm there. I just have to state the theorem I've already spoiled. So that's the theorem. The theorem is joined with Alex Puetz. We take a representation of the equivariant cycle. But here we do need some extra restrictions, which is, so remember, M was given by some Zn gradient vector space and a map, degree 1 map. So what we are asking for is that phi is nilpotent. Okay, so you compose phi with itself and at a certain point dies. So this is the case of all examples, well, of course there, and also that I've mentioned. So this class of varieties we studied with Fagin and Puetz. So such that phi is nilpotent. Well, we take E, whatever dimension vector, let me say reasonable in the sense that these quiver Grassmannians a priori could be empty sets. This I didn't mention. So I mean, there are confidence predicted of phi varieties as soon as they're not empty. So you could get like a bad dimension vector. But let's say you just assume that this does not happen. So for whatever E you take, then there exists an algebraic torus. Well, in fact, you can explicitly construct it, and n will depend only on the representation and not on E. So this n is the number of indecomposable summands of m plus 1, such that E and T is a GKM-Theory. And the corresponding graph, which is somehow, maybe I didn't make the point enough. So the corresponding moment graph is completely, let's say combinatorially. I mean, admits a purely combinatorial description, which was somehow the reason why is GKM theory was so successful for Schubert varieties. Right, because if you just know that in principle you can run this machinery, but you don't know the graph to start with, or you don't have a misplaced description, it's completely pointless. So it's completely, you can't apply it. And so, yeah, well, sort of, I'm very proud of this thing. I was actually very surprised that it would work with such generality, because you find a huge class of varieties. So you can use this, for example, to create certain, in that case, under some other restrictions, you can use this result to give a structure to the equivariant cohomology of certain quiver Grassmannians, has a structure of representation for certain products of symmetric groups. You can find sort of cyclic group actions on this and wonder about how it decomposes. It gives you a lot of structure which was sort of hidden. And the very last thing, because I really like this thing, so this torus is, so that's one way you can, in principle, produce torus actions on this thing. So you take your M, you look at the out group, and that's an algebraic group, you look for a maximal torus in here. This is bigger. So yes. So this is not entirely contained in the out of M as a quiver representation, because all the out group of N act on the variety, but you can have more automorphisms. And so there's one rank more that you add, which allows you to get the GKM structure. Otherwise, we tried first, of course, with a smaller torus, but then in that case, the number of one-dimensional orbits was a whole locus of one-dimensional orbits. And you add this S to C star, and fixes everything. So yeah, that's all I wanted to say. Thanks a lot.
Okay, are there questions for Martina?
So you had these families of one-dimensional orbits, you said. What do they look like, those families?
Without the extra C star?
Yes.
No, I am. Maybe I can tell you later, because it's a bit technical in the sense that
they weren't something interesting like just torque rise or price or projective spaces or something. And you needed the extra torque to resolve that.
Yeah, you see it from there, but I don't know what sort of varieties are. I can tell you, because it's fun, because it really comes from the structure of M. You really don't care about E. You have a way, so that's coming from quiver representation theory. So if you take a nilpotent representation of the quiver, of cyclic quiver, it always decomposes in a certain way. And you can, so these are sort of all strings of C goes to C goes to C goes to C goes to C by the identity and then dies. And that's all in decomposable summons like this. And somehow, so the first n-1 copies are just exchanging these summons. And then the extra copy is telling you where you are on a given string. So it's related to that, let's say. And so I don't know, but we have equations. So somehow you can really describe it explicitly. So that's the pretty thing. And so we also get, I don't know, cellular structure for this guy. So I find paving.
So it's smooth enough you get a cellular structure.
Yeah, exactly. Yeah.
Could you say a word or two on the combinatorial description of the graph?
Yeah. It is a bit related to what I was telling Frank about. So what you have is that the fixed points are. So okay, let me. I'll take an example. Okay, let's take delta 2. So what I was telling Frank is that, so an indecomposable representation of this guy is going to be something like this. So you take some C, which goes to C identically, which goes to C identically, which goes to another copy of C, and so on. So that means, and you can encode this into some diagram, which is that. So for any C, you do some, you have all these segments and strings looping around. This for any of the indecomposable summands. Then there's a way of arranging them in such a way that sort of the final arrow goes where you want. And the fixed points are corresponds to sub-diagrams of this. Which are, but it's, in fact, I can then give an example, it's very explicit. And so these are appropriate sub-diagrams where on the ith, here it was 2 and then more. Well, on the ith vertex, you take ei's dots, and the configuration you pick has to be, it's called successor closed. So you want that whenever you have a dot, you have all the following ones. And somehow, these are the fixed points. And then the one-dimensional orbits, so the edges of the graph, there's a procedure of cutting and paste. So there is some of this configuration which you cut a piece of your segment and you glue it to another one. But you can, in this case, you find back the symmetric group and transpositions. And so it sounds a bit tricky, but it's very explicit and combinatorial.
So GKMs for the torus action, and what I remember was that the sort of the equivariant formality was really key because that's the spectral sequence that generates an E2. But if you had some other, group action where you have that where you end up with an equivariantly formal space, and suppose you have finite fixed points, finite orbits, does the GKM stuff work with the different? I mean, I've always seen it with the torus, but I would guess it could work in more generality or not.
You can, there's also some results of Brion, right? Well, but then it's the nice case in the sense that if your torus is a maximal torus of a reductive group, and the group is acting on the variety, then you do the T equivariant and you take that Val group fixed points. So, but it's a bit of a trick. It's not that you're just working straight with the group. I mean.
If you have a larger group, you don't have a place to put your graphs.
Yeah, exactly. So here, I didn't say it. So here was just on the board. It wasn't on the. In principle, you work on the dual of the Lie algebra du torus, sort of a moment map where you are drawing your graph. I don't know. The only thing I saw was with somehow help of the torus anyway.
There's one more.
Hey, so if P is nilpotent, it sounds like you can take cover of delta n so that you can unfold P into a longer chain.
Yeah.
So that the last map is 0 or something like that. I mean,
it is somehow. It is
but
somehow
does it go
this.
back to example?
That's the way you construct somehow all indecomposable representations of this quiver. So you can just take one way of seeing it is that you work with sort of A infinity. Meaning really type A infinity quiver. You take representation, so just strings of C 0 0 at some point, and then you push it down. That's a way of constructing them. Yeah. But in fact, my hope was that one would manage to generalize it also to other quivers. That somehow we got still so many things to do here that we didn't try yet. So. All very welcome to try.
Well, let's thank Martina again for a nice talk.